When I say the word soil, what comes to mind? You probably think dirt, that soft brown stuff on the ground that stuff grows in. Well, you wouldn't be wrong, but there's a lot more to soil than that. Soil is a complex part of the environment, developed and changed by interactions with other components of the environment: rock, water, air, biology. You get different types of soils in different areas, depending on aspects such as the local climate, topography, geology, and human activity. And so the chemistry of soils are also different. Soils play an important role in many systems, including food production and ecosystem health. Geochemical analysis allows us to characterize soils, determine its quality, and assess soil processes, and is key to understanding the spatial variability, abundance, and distribution of chemical elements present in our soils. Many studies have mapped element concentrations and distributions, but what there hasn't been much of is quantitative analysis, which compare the presence of one element to another on a national scale. My research uses soil geochemistry data from across the US for geostatistical analysis, i.e. to find the correlation between 47 different elements to determine behavioral patterns. Correlation is assessed on scales -1 to +1, indicating the strength of the relationship between two variables. Positive values represent positive correlation, which means that as one variable increases, the other also increases. Visual or qualitative data, such as maps, can help in identifying visual patterns. But what about patterns which are not so obvious or clear to see? In my work, I took geochemical data from all these green points you can see in the first image to create element concentration maps, which were then used to determine correlation between each of them. You can see the colourful maps here in the middle, and the correlation coefficient for each pair written above. The coefficients for these three pairs are identical: 0.79, 0.76, and 0.78. A value of 1 would indicate a perfect positive relationship, and so as one variable increases, the other increases with the same magnitude. So the relationship for these three pairs is strong. The visuals, however, don't portray that relationship so well. I think the appearance of the top two maps look more similar to each other than the bottom two do to each other, and yet their correlation coefficient is identical. This demonstrates that quantitative data is vital in understanding patterns of behavior and underlying relationships. In identifying these large-scale relationships in soils, we can better understand element distribution, interactions, and behavior, and how element correlation relates to the environmental interactions mentioned earlier. You're probably now thinking, and? So what? Well, to put it briefly, healthy soil is essential to our survival. Now, I know that might sound a little dramatic, but it's true. And I encourage you to look up the impacts of soil and how life would be very different without healthy soils.